everybody. So in our lesson today, okay, which is why I have all these little puzzle cutout things. Today, looking at our chemistry triangle, Garrett, can I start last time we did our lab and we were focused up here, primarily on, we saw ionics, metallics, covalent. You saw what they did. They melted, they didn't melt, they were malleable, they weren't. Okay, today, goal is bridging this connection of based on what we saw with our eyes and what we know about how they look, why? Why do ionics take so much heat to melt? Why are they never malleable? Right, so getting down to the why behind these properties we saw, but we're only going to look at ionics and metallics today. We'll talk a little bit about covalence in the beginning, but outside of that, we're going to save that discussion for the next day because it takes a little bit more. But that's kind of your big objective of, by the end of today's lesson, you should be able to explain to me why ionics don't melt very easily. Or even within ionics, why one ionic would take even more than another ionic. So the comparison idea. Okay? So that's kind of why I have a bunch of, once again, little pieces, things, is to try to bring visuals to the molecular side. Because that's sometimes the hardest thing to bring a picture to, so I printed some out to help us. Okay? Jack, did you have a question?
About the retakes and corrections and all that, does that just mean that the online thing, that's like open until 6?
Yes. So if you're wanting to correct or retake your Unit 1 test, you have till midnight of October 6th. After that, the modules will close and you can't fix them anymore. As a reminder, because I know this is our first one, remember you don't have to do it with me. Technically, you can do it all on your own because it's all online. You submit your corrections, it opens up the retake. Please come see me though if you have questions, okay? If you're like, I corrected this one, but I don't really understand why, come see me and let's talk about it, make sure you figure it out, okay? But thanks for that reminder, Jack, that deadline is a week from today for correcting those unit tests, okay? Once again, your grade will be fairly stuck if you don't fix it. Because of how tests are weighted, and this is our only test on this term, I calculated that every point on the test is almost a 4% on your grade.
Dang.
So if you're missing only 2 points, that could prevent you from getting a solid A in this class because that drops you to a 92%, which is an A minus. So just be aware of that because if end of term comes and you're like, I want to fix my grade, there's not much at the end of the term you can do. Like you got to do stuff as we go. Okay, Bryson.
Wait, so with pathway 1, that's just like correcting the ones you got wrong on the sheet and just turning it in, right?
And then retaking the ones you got wrong.
Retaking them.
Yeah. So it's number for number. So if you, let's say you missed number 2 and 7 on the multiple choice, you're doing pathway 1, you just go retake number 2 and number 7 and leave everything else blank. Does that make sense? So when they get sent to me, I only look at those ones.
Wait, so hypothetically, like if we didn't turn in any of the tests, we would have 60%. How much would we have if we didn't do the test?
So tests are worth 55% of your grade.
And that's drops our grade 4%.
So you'd have 45%. Well, it depends on how many tests we have each term.
Okay.
That's why. But since we only have 1 test this term,
Then it's 4.
that's why it's so
Okay.
much. Yeah. Does that make sense? Yeah. Yeah.
So that first use, do we have to retake those in the test consider? Can we take them?
Nope, it's just on Canvas. Yeah, and then some of them, just because it makes it easier, because I made some that are self-graded now, so you can get most of your score back on the FRQ without having me to look at it. It's actually all on Canvas. You don't have to like upload anything. So you'll type in answers. Some of them are like fill in the blank or mathematical answers, stuff like that. So does that make sense? Yep, but you don't have to do any of it in here or the testing center. So, any other questions on retake corrections? Yeah.
Wait,
Yeah.
so there's 2 paths. The second one, you like retake the whole thing, right?
Yes.
What's like the benefit of doing that one?
You can do a second retake if you didn't get all your points back.
So the first one you can't take.
It's just one and done.
Okay.
Yeah. So yeah, but if like by chance like you retake it the first time and you do the whole thing and you're still missing 2 points, there's then a second retake. And I'll make as many retakes as you're willing to put in the work in for. So, does that make sense? Yeah, good clarification. Any other questions on that? Okay, let's take a look at this graph here as we talk about this idea of bonding. So in a covalent bond, so this is our only part of today that we're talking about covalence. But in a covalent bond, the way that it works, okay, so here's my 2 little baby hydrogens. Right, so nucleus and 1 little electron, okay. Hydrogen bonds with itself very often because it only has 1 valence, but it wants a full shell, and the first shell can only hold 2, so if it bonds with itself, like so, now they both have 2. So that's in a sense how a covalent bond works, is the electrons are shared, they overlap their orbitals, and now the two belong to both, so they both are full. Okay? What this graph is showing is it's showing that when this process happens for any covalent bond, there's an optimum distance for the nuclei to be. Yeah?
So like, why? So is the bond that they want to make stronger than the electrons repelling each other? Because they're going to be closer if they're both.
Yeah, but the bond brings in a stability more than others. Okay, so we have some extra guests, and they took your seats because you were late, so sorry. But, so one of you can go take that spot back there, and then we need to get a chair. Where's the best place to sit a chair? A corner somewhere next to somebody nice who won't elbow you. You can take this pen
Yes.
and just pull it up next to a friend.
Let's go.
Okay, glad you guys made it. Yeah, I don't know where's best. You could like, next to Levi kind of, these middle ones have more space in terms of the chair position. Can you slide next to you, Levi? I guess will your head be too bad?
I think I'll just like stay close, you know?
Okay, so everybody, first thing I want you to mark is this spot. The minimum on the graph is the perfect bond distance. And when we say bond distance, it's nuclei to nuclei. Okay, so I'm measuring from the nucleus. Okay? So x-axis is distance. Y-axis is energy. Okay? Now in terms of energy, the more negative energy a bond has, because we're talking about potential energy, the more stable it is. Okay? So first off, so from here to here, if I'm measuring this way, this is the bond length. Okay, so if this, I should have picked one like if it had distance markings, lots of times they will, so they have like a measurement of like 0.25 is the bond length. Okay? The y-axis is the stored energy. And the more stored energy in a bond, the more stable it is. Okay, so this is our stored energy. Negative energy means it's very stable and so it has a lot of potential to be used. Okay? So as we look at this graph, once again, you always look at that x-axis and the y-axis. So let's put some words to what we just said. Oh, let me do this first actually. So this right here represents this picture. Perfect bond distance between them. Okay? If I travel this way on my graph, what's happening to my bond length? Good, so traveling this way represents me pulling them apart. What happens to energy when the atoms pull apart? Good, so the energy gets less and less and then it eventually goes to 0. Notice that 0's up here for energy because we have negative energy as stored energy. So why would eventually the energy go away if you pull them apart enough? Is there a bond? No, there's no bond. And if there's no bond potential energy. So that's what this represents going that way is pulling them apart. So if on this side of your graph, maybe draw a picture of two atoms like far apart from each other to remind yourself. Okay? So then, coming over here, so here was our perfect distance again. What's happening to bond length if I go this way? So this means now I'm trying to push them closer together. So what happens with energy when they try to get too close? Spikes like crazy. Why would an atom not want to be too close? Unstable how, Christina? Sorry. They're good.
So like, as it gets closer, like the electrons are kind of like pushing on themselves.
Yeah, we get too much repelling too, also the nuclei, right? The nuclei are both positive. Two positive things don't want to be that close. So that's what this graph represents is what's the optimum distance? The optimum distance where they're far enough away that the nuclei aren't repelling, but close enough to still be classified as a bond. No matter what, so this line represents the hydrogen to hydrogen bond. All bonds will have a very similar graph where they will scoop down but then go flat. But the positioning of the bond length and the stored energy will vary depending on the bond itself. Okay? So if I were to like create a movie of like this like line, right? It'd be like up there, they're like on top of each other, and then as you come down the line, they like start going away, and then they get the perfect balance. And then as you keep going along lines, like getting further. Does that make sense? I'm trying to make an animation on the spot. Okay, let's put some words to what we just said. Okay, so this is just everything we went over. Once again, that bond length, okay, has that perfect minimum energy because it's now stable in that relationship. Let's move our other sample. Okay? In general, the stronger the bond, the shorter the bond length will be. Right? If it's a strong bond, they're going to be closer together than if it's a weaker bond. We'll talk about the variations that can cause that. So here's our hydrogen and hydrogen. Okay, is everybody good? Okay, so attractive forces, once again, we have kind of this push and pull idea, right? It's between all the atoms unless the potential energy minimum to a certain degree, but then they can't withstand when they get too close. Right, so if you try to push the atoms too close together, they're just going to push away because of the nuclei. Okay? In a sense, this is why there's no such thing as an argon to argon bond. Is because the energy doesn't work out for it. And so if the energy is not going to make it more stable, then it's not going to bond in the first place. So you would never see helium to helium on here. Or once again, bonds that don't exist, it's because their energy is too high. And so it's just not going to happen. Okay? As we look at it from a covalent side of things, there's two factors to consider. One is the size of the atom. The smaller the atom, obviously the closer the nuclei can be. If the atom is bigger, such as oxygen to oxygen, now this isn't a perfect model, I'll say, because oxygen actually bonds 2 electrons from each, but I can't model that with my picture here, so just play along with me. But if once again, if we're measuring circle to circle, that is much larger than that, right? Just because the atom gets bigger. Same thing if we bring in a third example. Where'd my chlorines go? Okay, so chlorine to chlorine, overlap and share, but the distance between gets farther away as the atom gets bigger. The second thing to consider is what's known as the bond order, which is how many times it's bonding. The more something bonds, the shorter the bond gets, but also the stronger, meaning more negative energy. Okay? So what I'd like you to do with your table buddy is taking this information, let's apply it, and on your graph at the top, you're going to draw 2 lines. Okay, based on what we just learned, I want you to draw a line for what O2's graph would look like. Once again, this is in relation to hydrogen, and then I'm going to change it because of the models change that to Cl2. Just because that's the picture I have up here. Okay, but show me how would the graph for Cl2 and O2 look compared to hydrogen. Talk to your table buddies. I'll give you 3 minutes to draw 2 lines. Ready, go. Think about x-axis and y-axis. Is it going to be more to the right? Is it going to be lower?
I just think it's that.
That's like oxygen. Probably
Then the atom has that energy.
So like past this point, it's stable but not perfect.
Yes, so things that don't bond are always going to be wrong.
But then if it goes below zero, it's stable, but then it looks like at this point, it's perfect.
Well, this is just for hydrogen. Yeah, it's just the depth of it would correspond with oxygen. We talk about is oxygen more or less stable than hydrogen. It's more stable than you can show below the hydrogen. If it's less stable.
So, farther apart.
Then consider your x-axis distance. Is the bond length for oxygen bigger? Possibly. I would take that into account. But your bond these are your two you know that further down on the like the answer, obviously there's kind of a square but it compares the why did you make CL2 lower
So like I did a little research section where it's
It's actually more about the order. Which yeah, because this is just the one for hydrogen. The key thing I'm looking for is imposition of what's there. Comparing to hydrogen, is oxygen going to be more left or right, higher or lower? I agree with that one. I half agree with your fourth. Depth. But your distance, I would work. Because it's all by the same. So it's going to be probably similar to another square. Yeah, order's like how many times you bond me.
okay. So order is just like a numerical value. It's not gonna be like 1, 2, 3.
Yeah, it's 1, 2, or 3.
Okay.
Does that make sense?
Yeah, so lower than more right.
It was kind of like, it was like I wasn't gonna go or
X-axis line, and you hit it right on the just run out. Yeah, I say that's fair enough. Once again, there's like somewhat of variance of what it could be, but they're like key components. Okay, let's talk through this and make sure we're on the right track. Now this idea of like interpreting a graph that's not there is something we'll do various times throughout the year on different graphs. The big thing when you're looking at a graph always is look at the axes, right? And take one axis at a time. So if I'm trying to draw the line for O bonded with itself, let's do distance first. So is O2 going to be shorter or longer than H2? Has to be longer, right? Like you can see it because the atoms are bigger. So I know for sure that the oxygen line should be more this way. Now the second thing to look at is the stored energy. Is O2 going to have more, less than, or the same stored energy as H2? Why would it have more? It's a double bond. So your oxygen line should be further this way and lower down than your hydrogen. Obviously it kind of varies how far and how low, but the big thing is bigger but more energy. Okay? Cl2 bigger or smaller?
Bigger.
Bigger than both, right? So it should be past where you put your oxygen. Stored energy, where would you predict? Probably similar to H. Maybe not exactly, but being that they're both single bonds, somewhere around the same. So that's kind of what we're looking for on these graph lines. If you drew 2 lines on your graph, even if they were wrong, have a smiley face for your effort, because I appreciate that. Because even if you're wrong, I'd rather have you be wrong and try something than just wait for me to give you the right answer, okay? Okay, let's talk now about ionics.
Slacking on the smiley face.
Mouse again.
So, with like the bigger ones, like the ones with more shells,
Yeah.
when they're closer together, I got a little dog that I wrote for, they still be sharing the base.
Only ever share valence. Yep. So, yeah, we never share. Yeah, good question though. All right, so now let's look at ionic bonds. So ionic bonds, it's different in the sense because they're not overlapping, right? It's not like we're sharing electrons. It's a full-on transfer, and after the transfer, one of them is positive and one of them is negative. So in this case, when we're looking at kind of the strength, or in a sense the energy of the stored relationship, the 2 factors we consider are somewhat similar though. Is we look at size, because the bigger or smaller things are, the closer they can get, and so the tighter the hole's going to be. So that's kind of similar in the sense of there's going to be more energy if the atoms are close. The other factor, though, to consider with ionics is the magnitude idea with Coulomb's law of the size of the charge. If I have one of these, so these are just representing like a positive and negative, but if this was a +2 charge, that's going to have a tighter hold on this negative than a +1 is. So those are the 2 factors we look at with ionics are size, the closer they get, the tighter they hold, and magnitude, the size of the charge. Okay, so this one I want you to do on your own, so not with your table buddy. Between these 2 pictures, so I have Na plus bonding with Cl minus, I have Ca2 plus bonding with Cl minus. Between these 2, circle which one is going to have a stronger interaction and then tell me why. Okay, I'll give you 2 minutes, try this one on your own. Okay, circle which one between these 2 bonds is going to have a stronger interaction and why. That helps. Here's the 3. Circle one and then justify why for me. Just a tiny little FRQ, doesn't have to be long, but why did you pick that one? Set your pencil down when you're done thinking. All right, if you're still writing, kind of write and talk at the same time. Turn to your table buddy and tell them which one you picked and why. Ready, go.
But I think it might be my
Okay, show me on your fingers. Did you pick number 1 or number 2? Show me which one you picked. Number 1 or number 2? Alright, the correct answer is number 2. Now, for those of you that picked number 1, once again, whenever you get something wrong, don't automatically be like, oh my gosh, like, it's not always bad. Because a lot of you, when I looked at your justifications, you had right components. It's just because really both factors are at play here, right? We have size and magnitude. When it comes down to it, the magnitude has a greater effect. And so that +2 charge plays a bigger role than the fact that sodium is smaller, right? Because sodium is smaller, so if you were thinking that, you're not like wrong in your logic. It's just in the comparison, a +2 charge is gonna hold tighter than a -1 and +1. So, questions on that?
Yeah, is it like the difference between the two, or just like 2 plus? Like, I'm not just, like, if it was Na plus and Cl2 minus, would that be the same as Na2 plus and Cl minus?
I would say then it's probably gonna be pretty similar. Yeah, so it's like, and that's often when they give you a question, they're only gonna change one factor, because it gets tricky of like, oh, well, if this goes up, but that goes down, which one could it be? But yeah, so it's like, or like if we had a third option, that was +2 -2, then that would be the choice, because now they're both gonna be stronger. Does that make sense? Yeah, great question.
When we were looking at periodic trends,
Yeah.
didn't distance usually have a bigger influence than magnitude?
So so that's the interesting thing about this, yes, is when we were dealing with like taking a valence electron, like ionization energy or electronegativity, yep, the bigger distance played a bigger role. But the difference here is that was being measured from like the center of the nucleus to the outside atom, right? In terms of this is just like when we're talking about distance, it's just like the proximity that they can get to each other, right?
As
Of
like a whole atom.
as a positive, yes, as a positive sphere and a negative sphere, like this distance. And so that's where getting bigger in size does push it away a little bit more, but not as much. But that's a great comparison, Alex, because it is like opposite.
Right,
Of what
and I
we're
mean, also, like, there's still electrons on both of them too that would be repelling, right? But like, is the overall force, it's like the protons,
Yep, it's
Like they
because there's that
balance.
unequal distribution, the overall force is positive.
okay.
Yeah, great comment question. Jeff.
So more charge, no matter what the charge is, as long as you have more of it, then it's going to be strong?
Yep, is gonna overpower a different distance. But hypothetically, let's say let's say this was a +1 charge as well, then this would have been my choice because it is smaller. So compare magnitude first, then look at distance when it comes to ionics. So, any other questions on that? Yeah.
Is that consistent throughout like all ionic bonds?
Yes, for any ionic bond. Yeah, I'd say that's true. Okay, so as we look at this idea of ionics, okay, we've mentioned it before, but as we visualize molecular level here, okay, that's what I want. Let's get our normal sodium. Right, so the way ionic is formed is sodium has 1 valence electron. Now we have a way in which we can draw ionics without having to draw the whole atom, because the only ones that really matter are their valence. So the simple way you can draw an ionic is just putting dots to represent how many valence it has. So there's a Lewis dot structure for an ionic compound. Okay, so sodium has 1 valence. How many valences does chlorine have? 7. So I draw 7 dots. Now it doesn't matter like exactly where you place the dots. You always place them in pairs, no more, because of orbitals, right? Because our bunk beds only have 2. And then you typically place them like in a T-like shape, not a diagonal, but it doesn't really matter. So when these bond, sodium gives up its valence because it has a really low ionization, right? It's not really holding on to it very tightly anyways. And on the reverse, chlorine has a strong pull because of its high electron affinity. And so they're like a beautiful, perfect match. They then bond together. Why do they stick together after the transfer happens? Because one is positive and one is negative, right? And so in the end, it would be, you can write it kind of like this, Na plus Cl minus, right? That's the end result after that the electron has been transferred. And that's in a sense how all ionic bonds are formed, is through this transfer. Now what we're going to get to next is the fact that this is a perfect one-to-one relationship. I have 1, you have 7, bam. It doesn't always work out in a one-to-one idea, but they can still bond with each other, but the ratios might have to change. So that's what we're going to look at, and what we have our little puzzle pieces for is helping us with this ratio idea. Okay, so if you don't have them out, go ahead and pull them out. If you have them out, put them in groupings of matches. So put all the +3s together, all the +2s, so on and so forth. Is anyone missing a bag? B6 doesn't have as many people, so. Yes. Oh, somewhere. We might have to go with what we have now. You're missing a bag? It's right here. Okay, no, I made just enough, no space.
Does anybody happen to have an extra?
Now, you might be missing some pieces, and so you might have to use your imagination. I was cutting as fast as I could, but I got a little short on my 2 minuses, so some of you are missing those. So, just pair them up for now, and then we'll explain what's going to happen. Okay? So, as we look at this concept, I'm going to explain it first off from the valence electride side of these. These 2 columns are getting to the same end goal. This is the goal. What's the formula? I'm just showing you 2 different ways you can look at it, kind of 3 with the pieces. Whichever process makes sense to you, use that one. I'll tell you first, my preferred idea is charges, but valence electrons are nice just to see the first time to kind of understand what's going on, okay? So we're going to do these ones together, and then we'll do the ones on the bottom of your paper for some smiley faces, okay? Where's my eraser? Okay, so the first thing to look at is when magnesium is going to bond with chlorine, how many valence electrons do they both come with? So how many does magnesium have? 2. So draw magnesium and put 2 little dots to represent its valence. Chlorine comes with how many? 7. So 1, 2, 3, 4, 5, 6, 7. Without saying anything, just to make sure we've all got it, make up a sign language way to show me how you find valence electrons. Do it now. How could you teach someone to do valence electrons? Like, how do I know magnesium has 2? Okay. Some of you are maybe doing it more complicated than what I do, because it's just the column number. Alright, so the column it's in is valence. Skipping
I drew the shells.
the D section. That you can do that as well, which some other people are showing as well, but it's going to take a lot more work to draw all the shells. So if you just count 3, 4, 5, 6, 7, right? That's how I know. I just want to make sure people knew where these numbers were coming from. Okay, so now, in order to bond though, the metals always wants to give up, the non-metal wants to give full. So magnesium can give 1 away, but it's not going to bond if it doesn't get the stability. So this ratio only works out if you have 2 chlorine atoms.
I drew that one too big.
Okay. So our formula for this is MgCl2. You need 2 chlorines for every 1 magnesium. Okay? Alright. Same problem, but let's look at it from a charges side. Okay? So magnesium has 2 valence electrons, so what charge will it always form? Close. +2. So the charge represents, in a sense, like what is it going to do? And a +2 means it's going to get rid of the 2 valence it has. Okay? So this is where, if it helps you visually, your little puzzle pieces can come into play. Now, mine I got from a while back are like labeled. So bear with me here, because some of them aren't like labeled right, but just pay attention to the charge, right? Like, because yours are blank. So magnesium has a +2 charge. Okay? What charge does chlorine have? So it has 7, so the charge is what it needs, so it's -1. Because it's going to take 1. So, once again, if you only have 1 of each, doesn't work out. So to make it balanced, you need 2 of these and 1 of those, because the charges must be 0.
We dropped it.
Okay? Questions on just either of those methods before you do some more? Now, ionics, for the most part, their names are very straightforward, because you just name the 2 things and add "ide" to the ending to show it's bonded. So magnesium chloride. I forgot to put mine in, so that's the name of it, is we call this magnesium chloride. nitrogen. Okay, lithium has 1 valence electron. Nitrogen has 5. So in order to get them, once again, lithium wants to give, nitrogen wants to take, so lithium can give 1, but nitrogen is still lacking in 2 spots. So in order for it to balance out, I would need 2 more lithiums. And so my formula would be Li3. And I would name it lithium nitride. Yeah, so you always end it in IDE. It's kind of like, I think of it as like they've been married and they changed their last name to show their bonding. So, okay, questions so far? Okay, I'm going to do this one, and this time I'm only going to do the charge version. Once again, you don't have to do both. I don't recommend doing both. Take whichever one works for you.
Yeah.
Okay, so this one I'm bonding iron and oxygen. How many valence electrons does iron have?
2.
So why is it a questionable thing? Yes, it's the transition metals, and the reason why they're called transition is it can vary. Sometimes it's 2, sometimes it's 3. So more information will be given to you because otherwise you have no idea. So that's what it is. We show it in Roman numerals is the way they chose to do it. So this is telling me that this particular iron, it isn't always 3, but in this case, the iron has a +3 charge because it has 3 valence electrons. So the Roman numeral tells me the charge.
Oh.
If they just said iron and oxygen, there's 2 possible answers because iron can be both of these. Okay? All right, but oxygen is a set one. What charge does oxygen always have? Yeah, so 2 negative is oxygen's always charge. So here's how I think through without the puzzle pieces. Okay? Is I know it needs to equal 0. So lowest common multiple between 3 and 2 would be 6. So to get 3 to be 6, I have to multiply it by 2. So I need 2 of these. And to get 2 to be 6, so Fe2, O3. Which is what you'd get if you built it out with the puzzle pieces. But questions on when there's a transition metal in the mix? Oh, for the name, the Roman numeral is part of the name. So you would name it as iron 3 oxide. You can't just name it iron oxide because, once again, it doesn't, if you had to work backwards, you wouldn't be able to work backwards from the name without knowing that Roman numeral. Okay, last one, it got cut off here because I couldn't read China. So the last one on your paper brings in one more component that looks a little weird, but if you treat it the same, is it Na? What's the first one?
CA.
I was trying to remember from last one. And then NO3, 1 minus. Okay? So the other thing to consider with ionic bonding is we sometimes have groups of elements that are actually covalently bonded, but they have a charge as a whole, so they then can ionic bond. Okay? The easiest way, though, is just treat them as a group. See how this is PO4, but it's still just one magnet? Just treat it as one thing. It's a bunch of things, but they just act as a family and they stay together. So that's what this is saying here, is you have NO3, but the whole thing has a 1 minus charge. Now, the valence electron doesn't work great for this because you're dealing with a group of things, which is why I blacked it out. But we can still go with the charge. So what charge does calcium form? Good, so calcium is 2+. We know this NO3 thing has a 1 minus overall. Right, so we have another +2 idea. Another -1 idea, so how many of each do I need? Yeah, 1 to 2. So to show it with a grouping, we go Ca parenthesis NO3 close parenthesis 2. treat it as a group and just throw it in parentheses. But notice that it's the exact same concept as MgCl. Okay? Questions on that one? Now for naming it, it's still just the two pieces. So calcium, and then our grouped elements have been given names. If you flip your page to the backside, there's a chart there with a few of them and the names. So find NO3, what's its name? So you don't do anything to its name, you just keep it as is, calcium nitrate. For now, you do not need to memorize that chart. I'm going to let you use it. You'll have it available. Maybe in May we will when we take the test, but I don't know if it's even worth it, to be honest. So it's more important to understand like how it works. So, okay, questions before I push you into the swimming pool? That reminded me of like Emperor's New Groove. You know that quote? I've been turned into a cow. No. Okay, try the next three. You can work with your table buddy. You can use the puzzle pieces, and let's earn 3 smiley faces. Ready, go. What's your question? Like CL2.
Like CL, one minus.
So we have 6.
Theoretically, your logic is in actuality, fluorine has such high maybe in the lab setting, just doing like consulting, like in nature, because again, they're forces of like whether they hold onto their electrons or let them go. A good question though. All right, try those 3 rows, and then we'll see how we're doing. How many of each did you use? Because it's not that what you're putting here was you don't need 2 F's and 2 L's. Does that make sense? It's kind of like reduce it. Yes, in the name, you do have to show the 2. Yes, hold on.
So
You can do it that way too. So how many valence does oxygen have?
and so if you have this,
So the charge represents what is it going to do with those valence? Is it going to give them away or try to give them away? So it's giving away. Oxygen has how many valence?
no, because it always has 6. It's just I don't know why I got 9, but it's just 2.
Give the 6 away or
I
5?
think 9.
And so that's why it's 2.
Wait, so for this one,
Does that help a little bit? So the charge is correlated to the valence electron. If you're doing this, it's just drawing the dots. It takes a little longer.
But it
Does that help for now? Okay, keep going. This one looks good.
then you call it aluminum oxide.
So we want these to add up to
Oh shoot, we have a 2.3.
number is 2. How do I go 3 and 6? Okay, so 2 males. And then how do I get it?
For iron, 2 oxide.
Portuguesa.
How I put the signs up. It's like I mean, there is like.
No, this is stupid. So is it just like, okay, NaCl?
inches is bigger. But yes, the format doesn't matter. When you write it, it should always be metal, non-metal. That is like the format. Good job, guys. That looks great.
Oh, wait.
Yeah, same. I think oxygen gas is like the answer to the
Okay, I've kind of walked around and checked roughly, but let's just make sure we're on the right track. Allie, did you have a question before I go over the answers?
Cyanide.
Okay. Now, with this process, everybody, okay, if it's a struggle, that's okay. Like, this is a hard concept to sometimes understand. So if you're like, I kind of get it, but I don't, like, that's why we practice and keep going with it. So it's okay to feel that way, okay? I just want to validate those feelings, okay? All right, the first one you should have said is Al2O3 is what you should have gotten, and its name would just be aluminum oxide. The second one should just be FeO, and you should have named it iron 2 oxide. And then the last one you should have Na2CO3.
Where's the parentheses?
So when you only have one of them, you don't have to put parentheses around it, but if you did, it's fine. It's just unnecessary information. It's like putting 1x. We don't write 1x, we just write x. But questions? Yeah? Maybe, so aluminum only has 3. Oh, so this one has 3. Oh, so this one is, how many more does this one want? Let's bring in another option. So you gotta keep going until they all get what they want. Can you tell me what charge aluminum they have? Well, how many valence does it have? So then oxygen, how many valence does it have? Plus 3 and minus 2. What number does that make sense? That's where, like, the valence method works really great for smaller things, but when they do get bigger, it gets a little trickier than see how it all fits together. Okay, so the last thing we're going to cover today, everybody, if you could put your puzzle pieces aside so they don't distract you, is now we're going to get into the whys of it, okay? So once again, we learned last time ionics have high melting points. They're never malleable, but they always dissolve and they always conduct electricity, but they don't do it when they're solid, okay? Now the question is, why does that happen? So we already mentioned this before, but let's add some vocab to it. Okay, so this once again right here, whenever I visualize an ionic, this is what you should be visualizing. Positive, negative, connected together. Now, because it's just full-on positive and full-on negative, there's actually no way of really knowing which one transferred the electron to begin with. Like, did these ones pair up and these ones pair up, or like this way, or like we're thinking 3D space and there's like one on top and one, like, you don't know which one it is. And so we don't often call this bond energy. We call it a lattice energy because you have positive and negative in all directions. It's not just like a one-to-one positive and negative energy. So lattice energy is just a fancy word to describe the bond energy in ionics. As we mentioned before, it goes directly back to Coulombic forces, meaning higher magnitude, greater force. Hence, NaF has less lattice energy than MgF2 because Mg has a +2 charge. So a +2 charge is going to give you a stronger force holding it together than a +1 - 1. And then the other factor, as we mentioned, you could also look at the distance or the size of them. That the closer they get, the harder they can hold. Okay? So we're going to talk through all the different ones, and you kind of just, what makes sense to you, you're going to add in, right, the justification of why these things are. So if I raise a hand, does anyone have an idea, knowing what we know now about ionics, why do all ionic compounds have a high melting point? Why does it take a lot of energy to melt something ionic? Rachel, what do you think?
Is it because they've got a lot of energy holding them together?
Yeah, because you got, once again, this is a flat picture, but like, there's a plus on top and a plus behind, on like all sides. And in order for it to melt, melting means pulling them apart. So it takes a lot of heat because you literally have to break the lattice, which is like tons of magnets linked all over the place. So it's going to take a lot of energy to do that, right? You're literally breaking the bonds away from each other. Okay, very good. Have a smiley face for what's up there, Rachel. Oh wait, they are though always soluble in water. Anyone have an idea why ionics, if this is what it is, why do they always dissolve in water? Yeah,
Because oxygen, sorry, is it because water is really easy to bond to?
Close. It's key with water, and if you haven't learned this yet, we'll spend the next few days learning it. But water itself is polar and has a positive and negative end. I should have made a little water molecule here. But the idea is, since water is like a magnet, it has positive and negative, it can come in, attach, because this is what it means to dissolve. But the water has to be able to link onto it, and it does it through a positive and negative way. So that's why they always dissolve, is because the water is positive and negative, and it can interact with the positive and negative. Thanks, Leah. I have a smiley face for that. Okay, questions on that? Any thoughts? Oh, let me say this and then we'll explain why. So conducting in a solid form, for those that aren't familiar with electricity, electricity is flowing electrons. That's what it is. Electricity going through a wire are electrons flowing. So in order for something to conduct electricity, you have to keep the flow going. If the flow stops, then electricity stops. I think of it as like, if something conducts, it's like crowd surfing the electrons across its surface. So any ideas of why it doesn't conduct when it's a solid? Bryson?
It's because it's a very rigid bond.
Yeah, and there's no movement. There's positive and negatives, but there's no movement to transfer the electrons with. So that's why as a solid, ionics will never conduct. It's too rigid, you don't have that movement. But once they dissolve, why then can it conduct now? Because the water has spread them out and they're moving with the water. So now you have movement of ions that the electrons can be passed between. Does that make sense, the difference? So in water, these are moving, which allow electricity to move. When it's a solid, they're not moving, they're stuck in their space. Questions on ionic? Oh, I guess we have one more malleability. Yeah?
When it's conducting electricity, so like, does the electron like have to like enter a shell and then like leave it? Like it kind of like goes around? Because if they all have full
It's
shells.
not really like going, it's just, that's why I think of it as crowd surfing. It's like going like, is the best way I can understand it and explain it. Yeah, but it's not going in it because they don't want another electron.
Right.
Right? But because they have charges, the electron can get passed through those charges to the other end of where you're sending electricity to.
Okay.
Yeah, kinda. Yeah, that's not a bad way to visualize it. So, okay, the last one, and this one was a question on your lab. Ionics are never malleable. What's the problem there? At the molecular level, why aren't they malleable? Corey?
Because if you move them, then you have two positives or two negatives touching, and they don't like to touch.
Right? They're gonna shatter. Right? So like you can shift them, but the shifting doesn't allow for the arrangement to stay. And so breaks apart every single time. That was my face for that order. Does that make sense? Questions on that? Yeah,
Why
here.
like metallic not do that?
Hold.
So that's
Hold that for 2 more slides, and then we'll talk about why metals typically then are malleable. Great question, though, Garrett. Any other questions on ionic? I apologize. If you feel like I'm rushing, I kind of am. It's a long time with our assembly schedule. But. Okay, we're gonna skip this for now. We'll come back to it later. It's just a practice problem. So now let's look at metals and their properties. So once again, this is a picture of a metal. Okay, all of the atoms are positive because they've all given up their electrons. And then the electrons move constantly, and you get that electron C idea. Okay, once again, there's really not that many electrons, but they're just constantly moving, filling the space. Okay, so let's go through the properties of metal. So I'm going to skip the next slide because I want to stay on the trend of properties, and then we'll come back to these definitions. So come here. So let's go to Garrett's question first. Let's start with the bottom of the table. Okay, so this is my metal. Here's the C. Okay. Why would metals always be malleable? Yeah.
Is it because the electrons are moving, so you can just bend it and the electrons will still flow?
Yeah, right. I can move these, and the electrons the C moves, right? It fills in the space, and so you can bend them. Obviously, some have tighter C's than others. Like gold is malleable, but like takes a ton of force to bend gold. But all metals with enough force, you can shape them, right? Some shape easier than others. But yeah, it's just that C helps fill in the holes. Yeah, great point. Have a smiley face back. Rachel.
Is it just like it's not locked? Like it's not like so tight together and like repelling that it only works in one configuration?
Yeah,
like photons can go however distance they want?
Yeah, like, I mean, there is somewhat of an optimum, like, they don't want to get too close because they're going to repel. But it's like, you know, like, they can move, and they can, like, slide, right? Even if it is, like, in a grid-like system, like, that can go there and it doesn't mess anything up. It just then would change the shape of your wire. So, yeah, does that make sense? Yeah, good clarification, Rachel. Bryson.
Is the reason why metals like shatter and stuff at like low temperatures because the electrons stop moving around?
You make it more rigid, yeah, and so then it doesn't have that flow. Yeah, that's a great connection. I've never even thought of before, Bryson. Okay, good on malleability. Okay, let's go back to the top. Why generally do metals take a lot of heat to melt? And some melt easier than others, but like in general, it's not as easy as our covalents. Based on our C model here, anyone by raise a hand have a theory for us? Why? Because they want to keep sharing, they want to keep moving. Because if they don't and they break apart, then not everybody's happy. In Unit C, we'll learn the difference between a solid, gas, and a liquid at the molecular level is this. Solid, liquid, gas. Like, that's all it is. And so if I'm going to melt something, it's trying to just pull these away, which then spreads out the electron C, which isn't really that full to begin with. Right? Like, there's really not that many electrons. They're just pretending they have enough. And so it's holding tightly and trying to prevent that from happening, right? So that's why. But thanks, Christina. Have a smiley face for that. Okay, solubility. Why would a metal never dissolve in water? Yeah, there's no way for the water to interact, right? The water can't penetrate the electron C, right, and like pull things apart. And so, yep, it's never going to dissolve. Thanks, Agla. Have a smiley face for that. Why are they great conductors as solids?
Because the electrons are already moving.
Right, the electrons are already moving. It's the best. Pass the electron along already set up. Right, so a new electron comes in, just gets passed along to the other side. Rachel, you had your hand up.
Yeah, because like the solubility in water, like why does water then like corrode metals and stuff?
So that's actually a chemical reaction that's going on with it. So the water's actually reacting with the metal, and there's like an electron transfer going on there. So yeah, great observation though. It is different than just like saying it's dissolving. So, okay, questions on our metals and their properties of why. Okay, let's go back to just some new words with our metals that we'll address here. So with ionics, we talked about like how to come up with their formulas and names. Metals you don't have to name, you don't have to write their formulas, but you should be able to possibly label what type of metal it is. So we have pure metals, which is just the same thing, right? Just like pure silver, okay, bonded to itself. You then can have what's known as a substitutional alloy. A substitutional alloy is when you bond two different metals, but they are similar in size. And so you still maintain somewhat of like a grid-like formation. Okay, a great example of this is, oh shoot, my mind just went blank. Copper and zinc, which make brass. Okay, so if you melt these two metals together, because looking at the periodic table, notice they're side by side, so they're going to be similar in size, right? And so since they're similar in size, you get a substitutional alloy. If there's a big difference in their size, you get what's known as an interstitial alloy, where the smaller one can actually fill in the holes between the bigger ones. Steel is an example of an interstitial alloy. It's a little weird, so I'll have to explain more of it later, but it's iron with carbon. So carbon is a lot smaller than iron, and so it actually fills in the spaces. Any ideas from an application side of why an interstitial alloy would be beneficial? Lily?
Would it be stronger?
Yeah, they're stronger. They're less malleable when you start filling in the holes. So that's one way to strengthen a metal that you maybe want, but then you put something else in it. Good. How's my piece for that? Any other ideas of why you would do a substitutional alloy? Like what would the purpose there be? Yeah.
You probably want a substance that like you can bend it, but it doesn't want to bend too far, kind of like clay.
Yeah, and lots of times it's like, I want the best of both worlds. Like, maybe this one's a little bit more conductive, but this one maybe I like its color. And so I'm going to blend them together and get rose gold, which is copper and gold melted together, right? So sometimes it's just you want how it looks, but sometimes it increases certain properties, makes it more malleable, less malleable, things like that. So we got 2 minutes. Final questions we have on these topics. Thanks for pushing through with me, everybody. Everybody give yourself a pat on the back and a smiley face.
This is all Brazilian and all that, you're like, let's
But it all connects. So homework tonight, you have 1 worksheet and then 3 AP question quizzes. Okay? So this is all ionic practice, so if you're like, I need more help with positive and negatives, the worksheet's for you. And then this is graphing, ionic properties, okay? If anyone would like to check out one of these, like if this really helps you and you want to check one out, let me know. I'm happy to let you borrow it. If it helps you in your I know those backpacks are
I think
The quizzes are like 3 questions.
Oh, they're only 3? Okay, so I got done with